You are welcome to tutorial 8. The topic before us in physics tutorial 8 is simple harmonic motion. And in simple harmonic motion, we are going to look at 5 different things here. The number 1 is definition of simple harmonic motion. Definition of simple harmonic motion. Now, simple harmonic motion is the to and fro movement of an object such that its acceleration is directly proportional to the displacement and it is directed towards a fixed point. When I say fixed point, what do I mean? The center of motion, the equilibrium position. For example, let's see this. Now, we'll have this retort stand, inextensible thread. You have to use inextensible thread because you need a particular length per time. And then this is the pendulum ball. Now, remember I said the to and fro movement of an object such that the acceleration is directly proportional to the displacement and is directed towards a fixed point or the center of motion. Now see this. This particular point where this pendulum is standing is the equilibrium position. Is the center of motion. If I displace it like this, it will move to and fro, to and fro, to and fro, like this. See, you displace it through a small angle. So you can see the to and fro movement that we are talking about. Now, let's see characteristics. The characteristics of simple harmonic motion. They are just two characteristics of simple harmonic motion. Number 1, the acceleration must be directly proportional to the displacement. Number 2, the acceleration must be directed towards a fixed position. What did I call that name for? The fixed position. The center of motion, the equilibrium position. Now, that is the 2 characteristics. Very quickly, I'd like us to look at some familiar terms you will meet in simple harmonic motion. And the first one is period, denoted using capital letter T. I remember, I promised us that I'm going to define period, I'm going to define amplitude in this tutorial 8. Now, let's quickly see that. What is period? Period is the time taken to complete one oscillation. Period is the time taken to complete one oscillation. Let's use this again. Let's use this again. Now, if I displace it from this point and it moves 1, 2, that is one oscillation. That is one period because it takes the time taken for it to cover one oscillation is what we refer to as period. If it moves to and fro, that time taken for it to move to and fro, we say is one period. That is the period for it. The period for it. Now, in this case, let's take note. We are mentioning oscillation. We have oscillation at the end part of this because we have amplitude and number of oscillation. Number of oscillation we are referring to here. When it moves to and fro, you have one oscillation. When you move to and fro, 2 oscillation. Let's quickly see this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 10 oscillation. Now let's take note again. Finally, the time taken for it to move to and fro, you call it period. The time taken to move to and fro once. The time taken to complete one oscillation because that is one oscillation. Now I've done that definition. I'd like us to see the relationship between period and the time we talk about. We'll have period T is equals to small letter t all over number of oscillation. We'll have it inside, we'll see it later. Now, that is for period. What about frequency? Frequency is the number of oscillation completed per second. The number of oscillation completed per second. Now, if you have this displays, and you have maybe 32 seconds after 20 oscillations, to get the frequency, you divide 30, the number of oscillation, which is 20 divided by 32. if you have 20 oscillation in 32 seconds, 20 divided by 32, you have the frequency. Frequency is the number of oscillation per second. Now, frequency, they use capital letter F, small letter F to denote that, small letter F to denote frequency. Now, let's quickly see amplitude. Amplitude is also important. Amplitude is important. Amplitude is the maximum displacement of a particle from its equilibrium position. From its equilibrium position. Let's quickly see this. Assuming I have a record stand like this. I have a record stand like this. And this is the ball. This is the pendulum ball. If I displace it to a small angle and I free it, it will move to this other point. If I trace this down, trace this, and you draw a line like this, straight line, horizontal line. The distance between these 2 points, you call it the amplitude. The amplitude of motion. The distance between that point, you call it, remember we say amplitude is the maximum displacement of a particle from its equilibrium position. Can you see the equilibrium position here? Displace it from here to this point. Now, that is for amplitude. Number of oscillation, we've explained that. We've explained that. It moves to and fro is 1 oscillation. That's how you count it. When we get to practical aspects, we'll deal with that squarely. Now, very quickly, let's see formulae used in simple harmonic motion. The basic formula in simple harmonic motion, take note, is period, capital letter T is equals to 2 pi square root of L over G. Let's take a look at this. This is the formula I'm talking about. This is the formula I'm talking about. The main formula for simple harmonic motion, period is equals to 2 pi square root of L over G. And we'll have frequency is equals to F, which is equals to 1 over T. Now let's check this, because I remember promising us that I'm going to show the relationship between period and frequency. If we have period to be equals to small letter t over n, remember frequency, we define it, we say it's number of oscillation per second. Now we'll have number of oscillation all over time. If you multiply, if we say this one is equation 1 and this one is equation 2, if you multiply equation 1 by 2, it means I have Tf is equals to T over n for T here, because what you do to the left hand side, you also do to the right hand side. Multiply by n over T. N can cancel n, T can cancel T. From there, I have Tf is equals to 1. If I make T subject formula, which means divide both side by F, divide both side by F, this will cancel this. So finally, I have period is equals to 1 over frequency. That is how to derive the relationship between period and frequency. Now, that formula you see there, look at it here. If you make frequency subject formula from this formula, you get this. That is how we show that. Now, remember we're talking about formulae. We'll have angular speed equals to 2 pi f. At times in question they call it angular velocity, so take note. They call it angular speed, angular velocity, know what they are referring to. Are we there? Now, this is 2 pi f, this f is frequency. Now, check this, frequency here is 1 over t. If I put 1 over t in place of frequency here, I have this formula. So we are just using one to generate another. Now that is it. Let's see this one. We'll have linear velocity or tangential velocity is equals to angular velocity times radius. Angular velocity times radius. Did you remember this radius we are talking about? If you don't, you can't recall, I'd like you to check tutorial 7, physics tutorial 7 to see that. Now, at times, instead of giving us radius, they mention amplitude. If they mention amplitude in question, know that they are referring to radius. Now, and then we'll have f is equals to n over t. You have seen this before. Look at it here. T is equals to, capital letter T is equals to small letter t over n. You have seen it before. This is it here. Now, let's see one good and hidden equation. Good and hidden equation in simple harmonic motion, which is this. Period 1 square over L1 equals to period 2 square over L2. Very important. In order to throw more light into what we have just explained, let's solve some questions and then see. Let's solve some questions. I'd like you to take a look at what we have here on the board. I hope you are okay with them. We can rub them off. Now, let's quickly look at the question we just talked about. Now, let's see. Example 1. A body executing a simple harmonic motion has an angular velocity of 40 radian per second. So, the angular velocity here, we're on example 1. The angular velocity is 40 radian per second. If it has a maximum displacement of 6 centimeters, remember, what's the meaning of maximum displacement of a particle? They are referring to amplitude. Maximum displacement. That is, it will be R, it will be A, 6 centimeters. Now, I don't need to use 6 centimeters. I need to convert it to the SI unit, International System of Unit. Now, which is, if I convert it to meter, you convert from centimeter to meter by dividing with 100. So 6 over 100. I have 0.06 meter. Now the question is, calculate its linear speed. Linear speed, remember? Linear speed. Now linear speed V is equals to equation. We'll have V to be equals to angular speed times R, which will be equals to E. Now I have V is equals to 40 times 0.06. Now if you do this, just take it to be 4 times 10 times 0.06. It will give you 4 times 0.6. If I use the 10 to multiply by 0.06. Now, I have 0.6 here. It's still the same thing as 6 over 10. Now, if I do 4 times 6, I have 24. 24 divided by 10. I have 2.4. 2.4, what did I calculate? Linear speed. So I have meters per second. That is the speed that we are looking for. That is the speed that we are looking for. That is the speed that we are looking for. That's example 1. You can pause to still take a look at it. But let's go to example 2. Now, in example 2, we have this question. A simple pendulum, 0.6 meter long, has a period of 1.5 seconds. A simple pendulum, 0.6 meter long, has a period 1.5 seconds. What is the period of a similar pendulum? 0.4. So, what is the period of a similar pendulum? 0.4, that is the L2. 0.4 meter. Now we are comparing oscillatory motion here. We are comparing oscillatory motion. Remember, I asked us to record the last formulae I showed to us. Now we are going to use this. T1 square over L1 is equals to T2 square over L2. What am I looking for? T2. Make T2 subject of the formula. I have T2 is equals to T1 square over L1 times L2 square root, because I have square on this. So if I substitute, what is my T1? T1 is 1.5. So 1.5 square all over. What is my L1? 0.6 multiplied by my L2, 0.4. So if I do the square root of the whole of this, what do I have? 1.5 square. I can bring it out to have 1.5 root. The value I have here, 0.4 over 0.6. And this value you have here, if you break this down, if you divide 0.4 by 0.2, you have 2. 0.4 divided by 0.2, you have 2. 0.6 divided by 0.2, you have 3. And this is your final answer. Remember, T2 calculated in seconds. That is the final answer. Now, I want to ask you one question here as your assignment. One question as your assignment. I'd like you to listen carefully. Listen carefully. Now, a simple pendulum, that's your assignment. A simple pendulum has a period of 17 seconds. When the length is shortened by 1.5, its period is 8.5 seconds. Calculate the original length of the pendulum. I take it again for the last time. A simple pendulum has a period of 17.0 seconds. When the length is shortened, we'll have a full stop there. Full stop there. When the length is shortened by 1.5 meter, its period is 8.5 seconds. Calculate the original length of the pendulum. Calculate the original length of the pendulum. And your expected answer is approximately 2. Approximately 2. Approximately 2. Now, thank you very much to subscribe onto this physics tutorial. I would like us to move straight forward to tutorial 9. I'm going to solve this question in tutorial 9. I'm going to solve this question in tutorial 9 before we start. Thank you very much. Subscribe. I know you have questions to ask us. You can email your question to jeromeonuche@yahoo.com. Jerome Onuche@yahoo.com. jeromeonuche@yahoo.com. I know we may not be able to answer all the questions, but we'll try our best. In case you are in need of physics teacher, why not? If we are close to you, we can push one good physics teacher to you. Thank you very much. Let's move forward straight to the next tutorial, which is tutorial 8.